To the course. So next week, I hope, is going to be the midterm. Okay. The smart week is when we put all the extra stuff. So should try to do the midterm next week, Tuesday, Wednesday, or Thursday. So hopefully we will fix the time. So I think there was a possibility of Friday, right? But if everybody can do it on Friday, then we can do it on Friday. So within a couple of days, I will fix the time for the midterm, so it will be sometime next week. Today, I want to talk about data abstraction. This is very important. This is a kind of refresher from 1104. But since it's so important, I think it's important that you really understand, and especially the special kinds of abstractions, functional objects, for example, and stateful abstract data types, which are kind of exotic, and also how to build secure abstract data types. So there's abstract data types, there's objects, but in fact there's 4 kinds in all. And there's a couple of exotic ones. And that's important to understand because more languages are starting to use these. And also how to build a secure abstract data type. So you cannot break the abstraction. So I'm going to explain that. And then the second part of the course today will be on multi-agent programming. So this is basically using communication channels. So remember we saw these communication channels called ports. We can build them into kind of agents, which I call port objects. There's also another kind called active objects if they use classes inside. And then I want to compare this with deterministic data flow. So you know, in this course, it's very important to understand that we start with declarative programming and the power of declarative programming. And one of the powerful paradigms is deterministic data flow. So I want to compare it to active objects. It's very important to understand how to compare the paradigms. So I'm going to give you an example of a problem we're going to solve, and we're going to compare them. This is actually a very interesting problem. It's called Flavius Josephus problem. And there's actually a guy named Flavius Josephus who was a historian 2,000 years ago. And he wrote some very interesting things. And so one of the things he wrote is going to be the basis of this interesting example. So we can do that today. Okay? So this we're going to use Flavius's ideas to compare deterministic data flow and active objects. So you can really understand what they mean. Because it's very hard really to compare them. They're very different. But once you can see the same application in both, you can actually make connections between them. Okay? But first, let me talk about data abstraction today. So, data abstractions. So, this is very important, and I'm going to go farther than I did in 1104 in the previous course. I want to go more to the foundation. So there's 2 kinds of data abstractions, fundamentally different, objects and abstract data types. So if you remember in the previous course, you maybe might remember a bit, but I will refresh your memory, and then we will go a little bit deeper into it. So each of these 2 can be declarative, so pure functional, or non-declarative, which means it uses mutable state. So that makes 4 kinds of data abstractions. okay? So we're going to show how to define all 4 of them, and especially we're going to show lexical or static scope, higher order programming, and a new concept called an unforgeable key. So in Oz, this is called a name. This is a constant that cannot be forged. You cannot fake it. And with this, you can build secure data abstractions. So with these concepts, you can actually build all 4 of them. Okay? So it's important to see how that's done, I think, to really understand it. So let me define first data abstraction. So this is a kind of refresher. So a data abstraction is part of a program, and it has an inside and an outside, which is the rest of the program, and an interface. So here's an example. So this is code in here and here. So this code does not have to be together. No? It can be in different files spread around, but conceptually it's part of the same abstraction. Okay? And the inside is hidden. You cannot see it from the outside. And the only way to access this data abstraction is through the interface. So this part here, which is a set of operations that you can use according to certain rules. That's the only way to access. You cannot go in and mess around with the code or whatever inside here. Okay? So this is important because it means you cannot break what it's doing, and you can only access it through the interface. So the programming language has to support that. And some languages support it better than others. A language like C or C++ has basically no support because you can look inside and do anything you want by doing casting. So C++ is very bad in this regard, but a language like Java is much better because you cannot go inside and look. Within the language, if you go outside of the language and start mucking around in the files, then you can look at things. But within the program, you cannot do that. Okay? So that's the abstraction. So we're going to show how to build it. So I'm going to use a simple example, a running example, which is a stack. Okay? So a stack is a nice kind of data structure. So here I'm going to implement the stack with a list. So a new stack is empty, so that's nil. If I push X on the stack S, I get X bar S. So it's a list, and the first element is the top. If I pop the top element, then X will be equal to S dot 1, which is the top. Now S is a list, and the result is S dot 2. Now remember that lists, the left and the right parts are actually tuples, so they're number 1 and 2 in the fields. And finally, I can have a check whether the stack is empty, is just comparing to nil. So this is a stack, but this one is not encapsulated. Okay, it's not protected. That means anybody can go inside and look inside here. So it's implemented using lists. So anybody using this stack can muck around with it. I can fake a new stack. I can do things with the list. I can reverse the list, which I can't really do in the abstraction, okay? So if I use this implementation, I cannot guarantee that it's used correctly, okay? Any program can mess around with the insights, okay? So that's the reason why we need to protect the internals. So you see, this is the basic example. So this is not a data abstraction, because it's not protected, it's unencapsulated. Okay, so now we want to protect it. We want to make it so you can only access through doing some operations. So there's 2 ways. So the same stack, we're going to show both ways. So it's important to compare the 2, because they're actually very different. And if you do a mathematical study of languages, you see they're actually quite different. They're fundamentally different, okay? But you can do the same data abstraction. So the same stack you could make it object or abstract data type. Okay, so there's two kinds of data abstractions called objects and abstract data types. So an object, there's only one kind of thing. So this groups the value and the operations in a single entity. So you have one thing and you can send operations and then transform it. But an abstract data type has two kinds of things: the values and the operations. So if I have integers, 5 and 6, I do 5 plus 6. The 5 is just a value, and the plus is an operation. Okay? But in an object, the 5 would already have the operations inside of it. There would not be other kinds of things. So if you use a programming language like Smalltalk, if you ever used Smalltalk, or Squeak, if you've heard of Squeak, which is a modern version of Smalltalk, everything is an object, even the integers. So if you want to do 5 plus 6, you have to send a plus 6 message to the object 5. Okay, and then you get another object, it becomes object 11. So you only have objects. But in fact, there's two kinds. So typical example in the real world. So this is actually something you can see in the real world too. Like a television set or this computer or a mobile phone. Television is maybe an old example, okay? This is an object because everything is in one kind of thing. It has an interface, buttons and things and controls, but there's only one kind of thing. But if you have a vending machine, which gives you soda or something, Coca-Cola, then it's an abstract data type, because you have the machine, and then you have coins, and you have the soda can. So you have different kinds of things. You have the values, which are the coins and the cans and the machine. There's two kinds of things. Okay? So these are naturally different. Okay? You could combine them in weird ways. You could have a television set that only works if you put coins inside, but you can have like a pure object and a pure abstract data. Okay? So let me talk first about abstract data types. So there's a set of values and a set of operations, two kinds of things. So typical example, integers, 1, 2, 3, and operations, plus, minus, etc. You know that in a language like Java, you actually have numbers as abstract data types, but also you have them as objects. That's kind of a weird thing for Java. You can take numbers and convert them to objects and back to values. Why does Java do that? Well, because Java is coming from C, where the integers are abstract data types, and the abstract data types correspond to what the microprocessor is able to do directly. So for efficiency, for simplicity, they add that. But since Java is an object-oriented language, they also add integers as objects. So that shows you kind of a weird thing, but you can see that the same kind of data can be both things. So usually, these two things are constant. So there's no state here. That's the interesting thing. There's no state at all here. Nothing is modified. It's purely declarative. So these values cannot change. 2 is 2. And the operations have no internal memory. Plus is the same piece of code and won't change. Okay? So this is all purely declarative. Okay? So let's implement a stack as an abstract data type. So the values are values of the stacks, a particular value of a stack, and the operations, we can define these 4. New stack, push pop is empty. So an operation will take a stack as an input and an element, and it returns a new stack. Okay, so a new stack is here a function that returns an empty stack. Push will take a stack S, an element, and return another stack. Pop will take a stack S, an unbound variable X. It will bind X to the top, and it will have S2, which is the pop, and so on. So then you can do these kinds of operations, huh? I take a new stack, I push A, I push B, and the stack S will be BA, B on top. And if I do pop SX, then X will be the top, huh? It will be B, and the returning stack will be just A. Here I'm representing them as lists, huh? So this is the stack as an abstract data type, okay? But this implementation we saw before is not a data abstraction because it's not protected. Okay, the stack is represented as a list. So we want to protect this. So this is something I want to specially talk about today, is this notion of this protection, okay? How can we protect this and make it a true abstract data type? So the way is we have to protect the values. We have to make sure that nobody can see the stack values except the operations. So how do we do that? Well, we can do a kind of encryption if you want. We can take the value, we can encrypt it and make some kind of box which is encrypted, and then to unencrypt it, only these operations will have the key. We'll know the key for encrypting and unencrypting. So that's basically the idea of a secure abstract data type. So it will be very close to some kind of an encryption, okay? So we will define two functions, wrap and unwrap, which you can call them also encrypt and decrypt. I say wrap because it's like you're wrapping the value. So wrap is a function given a value, will returns a protected version, wrapped version, and unwrap will take the protected version and return the value. So unwrap and wrap are special functions, and inside wrap and unwrap there's a secret key. Okay, we're going to show how to implement these. There's a secret key, and so wrap knows the key, so does unwrap. So the stack operations will know these two functions, but nobody else knows them. They will be hidden. And we will use lexical scope to make sure that they are only known by the operations in the abstract data type, okay? So this is, you can see it like they're doing encryption and decryption. They don't actually have to do that in the language, okay? But they could. If you want the value to be protected, even from people who look at the binaries, you can actually do an actual encryption, okay? But in fact, you don't have to do an actual encryption in the language. You can do something simpler. But if you do that, then it's not actually protected. The binary is then not protected. Huh? But from the language viewpoint, it looks like encryption and decryption, okay? Now these functions are special. Huh? They know a key. That means each abstract data type that we make has to have a different key, of course. Huh? Because if you use the same key for all of them, then they're not protected. Then you have like public, it's not protected. So you have to create a new version of wrap and unwrap for each abstract data type with a new key, okay? So that's very important. So we will have a procedure, new wrapper. When you call this, it actually defines the two functions. Because inside of new wrapper, you're going to create a secret key. And these two functions will know the secret key. Okay? So that's the idea. And I will show you how this is implemented in the language, so you understand exactly how it works. Okay? Okay, so what we're going to do here then is called secure encapsulation. So the language, the programming language has to support it. Some languages do not support it, like C or C++ or JavaScript, which are basically messy things, okay? I don't really recommend using them for big applications. There's better languages today, like Rust, for example. Java is also better because it has real encapsulation. So if you are using a language, you should ask yourself, Can people break my abstraction? Okay. So the language has to support unbreakable abstraction boundaries. That means nobody else inside the program can do usual language operations to look inside. Okay, in Java, it's impossible to look inside a primitive type, like an integer. You cannot see the machine, how the computer is actually representing it. So it's completely protected. But this is not true in C or C++. In C++, you can do a cast, and you can even look at the stack. You can look at everything. You can really, and you can see exactly what's going on in terms of machine instructions. So it's not protected, okay? It looks like you have abstractions, but they're not really abstractions, okay? So this is important, the language has to support it. But if we want to make abstract data types, we need a special concept in the language. An unforgeable secret, a key, a value, which is a value, like a constant, like 1, 2, 3, but that you cannot forge. That means if I don't know the value, I cannot create it. Okay? Integers, of course, are not like that. I can take the integer 25, and any program anywhere can make 25. So it's not unforgeable. So I need a special kind of constant that cannot be forged. Okay? So we have to add that constant to the language. Okay? So we're going to add two concepts. So first of all, the unforgeable constants, and second of all, a box that you can open with a key, which I will call secure records. So there's actually two concepts we add. The keys, and then the boxes. So this is actually very interesting, because many languages do not support this, or do not give it to the programmer. They might have it internally. Languages that let you build abstract data apps will do this inside, but they might not let the programmer look at it. So here in this course, I want you really to understand. So you will see these things. We're going to program this demo. So the unforgeable constants. This is a very unusual kind of thing. Most languages that you use will not show that to the programmer. They might have it internally, if they have some kind of protection or key, but the programmer has no way of getting to it. It's hidden inside. But I'm going to show it to you here. And this is a very special, weird kind of thing. So in Oz, this concept is called a name. And there's a function called newName that creates a new, fresh name value, so an unforgeable constant. So this value n, you cannot print it. You cannot guess it. If I try to print this, it will just say name. It will not, there's no print representation for this, a string or whatever. Integers, you can print them, 25, 25, you print the integer. And if somebody sees that, you can create the integer 25. You can print it on a piece of paper. But a name cannot be printed on a piece of paper. You can store it in a file, but only as a file that contains language values. So a text file cannot store this. Okay? So it's a very special kind of thing, And then the second one is the box, which is a secure record. So the way we're going to implement it, we need a box that we can lock with a key. So the name will be the key, and the record here, it's the box, it's actually going to be a record. You know, records already let you combine things. With a record, you can combine fields together. But records have lots of values. You can find out, you can print them, you can find out what are the fields of the records. But these records are very limited records. There's only one operation. Well, two. You can create them, that's one operation, and you can access the field with the dot. That's all you can do. You cannot do arity, you cannot find out how many fields there are with width, you cannot print them, you cannot do anything except dot. So it's like a very limited form of record, okay? And in Oz, these are called chunks, okay? So Oz has these two concepts that were added so that you can build real secure abstractions, okay? So in Oz, this is called a chunk, okay? And the idea is you can take any regular record, R, any record, and convert it into this secure record. So this chunk is a limited record that you can only do dot. So the dot lets you access, but it will not tell you what the fields are. It will not tell you anything, but you can do C dot something. That's what you can do, and that's all you can do, okay? So these are, you can see them as a limited form of record, but you can also see them as a box with a lock that you can key, or a room with a lock on the door, okay? In order to get in, you need to have the key, okay? So with these two concepts, we can build wrap and unwrap. So the only thing language has to provide is these two, okay? And then we can make it so that it's provably secure. So here's one way of defining wrap and unwrap. So here, this is new wrapper. So first of all, we create a new name. So this is a key. So I call it key because it's like a secret key. Notice this key is only known inside the scope of this procedure. It's not known outside. And now I define two functions. So wrap of X will create a chunk, but it will have a record. So I use a very simple record here. A W, which is the label, key is the field, colon X. So it's a record with only one field, which is key. But you can add more information if you want. You can add metadata, you can make this more complicated. But this is very simple, it will only do the wrap. So basically I take X, I put it inside a record, and I convert it to a secure record. So the only way to access X is to do the chunk dot key. So the only way to get back the X is to know the key. So unwrap will just do W dot key. So W will be one of these chunks. So this is a secure record. And the only way to access the element here is to do dot key, okay? So I know the key. So this is provably secure. The key is unforgeable, and it is only known in this part of the code. Nobody else knows it because of lexical scope, okay? So these two functions will know internally the key. So you can see the key is actually part of the contextual environment of these two functions. So you can see this is actually an example of higher order. So the contextual environment is like a hidden environment inside of a function. So we're actually using that to store the key. And someone who knows wrap cannot find what the key is. It's impossible. And if you know unwrap, you cannot find what the key is either. It's impossible, okay? So these two functions, they both know the key. It's shared. They have this access to the key, both of them. But nobody else knows it, okay? Nobody else knows it. Okay, you can actually make it a little bit more robust. What if somebody makes a mistake and tries to access W, a key that does not exist, or the wrong, or W is the wrong thing, it does not have a key? Well, this will raise an exception. So I can handle this and make something nice, okay? So you could make this nice so it does the nice thing, it gives you good error messages and stuff. If you use it wrong, you can assume that people will make mistakes sometimes. So you can do that, but it's still completely secure. This exception will not expose the key. The key is not in there. The key is never an output here. Huh? I mean, if you made a mistake, the programmer has some responsibility. Huh? If you output the key as a result of the function, that's stupid, because now the key is known. But here the key is never output. Huh? And here neither. Huh? Okay, so once we have this, we can actually build a true stack abstract data type, one that's completely protected and there's no way to break it. So here is our stack, our trusty stack. We're going to put it inside a local end. So I'm going to define two local variables. So the identifiers wrap and unwrap. But they are only known here. Nobody else knows them. So notice the static scope or the lexical scope is super important here. So your language has to support lexical scope. But that's okay. Most languages today, they do support that. It's very important. So when I do a new stack, so nil is my empty stack, but I call wrap of nil. So I'm going to return a protected new stack. Now if I want to do a push, I want to push X on the stack. Well, how do I do that? Well, first I have to unwrap it. So I call unwrap of W. And then I do X bar that. So I put X in front. And then I wrap it again. So basically, one of these functions, when you come into the function, the first thing you do is unwrap. Okay? Then you do your operation. And before you leave, you wrap, you put it again. So this is very normal. It's like what happens in a bank with a secure box. So what happens, if I have a secure box, like a safe, and I'm carrying it around, and I bring it to the bank will go to a secure room. So this is like a secure room. They will open it with the key. So that's the unwrap. They will look at the papers and stuff inside. They do something, sign the documents. And then they close it again. And again, they lock it. So before you leave the room, you call wrap, you lock the box again. So this is very much like the way banks and secure organizations handle secure data. If I have what's called a diplomatic pouch, I want to send secret information to the Belgian consulate in Russia, for example, I will do like that. I will have a box or something which is sealed, and I will only open it locally in a secure place. And then I close it, and when the box goes outside, it's sealed, and when it arrives at the other side, they will put it into a secure room again, and they will have a shared key, and they will open it. Okay? So this behaves in the same way. Okay? But inside your language, you can see that it's inspired from real-world secrecy. But this works very well. So push and pop. Pop also, it will first do unwrap of W, so that's S. X is the top, so then it binds X to S.1. So that the top of the stack, it's given out, it's not encrypted. And then I wrap S.2. I again lock the rest. Okay? So I always have wraps and unwraps, except here is empty, I'm only checking something, I'm not creating a new thing, so I only have unwrap here. I do unwrap W and then I compare to nil. So from the outside, there's no way to see that these things, what's inside a stack, no way to see, they're hidden. So wrap and unwrap are hidden from the rest of the program, okay? So I want to show you this, I want to show you some code now, how it works. So it's important to run this stuff and to see how it works. So for example, okay, here I do a browse of 25, and I see the 25 here, okay? But let me show you how names work now. So I create an identifier M with a variable, new name. So this is an unforgeable constant. Okay? So what happens if you browse it? If you try to show it? Well, the browser knows that it's a name, but there's no print value. It will just say this is a name, N. Okay? And so this has no print value. You do not print it. If I create now another one, N2, for example, this is another name. Okay, if I do browse, I see it's a name. So N and N2 are two secret keys. They're unforgeable constants. So I can do something, I can compare them. That's what I can do to them. I can see, are they the same? No. False. Is N equal to N? True. Okay? So I can compare them, and I can see they're different or not different, but I cannot actually look at the value. So how do I do this? How does the language do this? Well, it does it. It's part of the language semantics, okay, that this does not have a print name. So when in the language semantics, remember I sometimes use these Greek letters for the constants. So when I create a cell, for example, the name of the cell will also be a name, but it's a semantic thing. They exist in the semantics, but they don't have any print values. There's no way to bring the value outside, okay? And there's no way to forge it. If I don't know the value, there's no way to create it. So the only way to get the value is if somebody gives it to me, okay? So I can do a new wrapper. Call this wrap. So I will first create a new name, okay? So my keyboard has some new problem. So let me do a wrap of some value x. So here I will do a chunk. So I will, some record, the field name will be the key. So here I have a record, I just create some record, but the interesting thing is the name of the field is key. So records are allowed to have these funny constants. They can be the names of fields of records, okay? And chunk will convert this record into a limited record, which I call secure record. And the only thing you can do with one of these chunks is do dot operation, okay? So here I do dot fw dot field. Okay, so that's it, So this is actually very simple, Once you have the names and limited records, then you can build these wrap and unwrap. So how come it works? Well, this is the language semantics again. The language is designed that chunks do not have almost any operations. It's part of the language design. Okay. So now I can create a pair of these. Okay, now I create them. So I call new wrapper now. Oops. There. So these are functions, If I have now, let's say W and X. Let's say X is equal to 23. Okay. Browse X. We'll browse 23. But now let's say W is equal to wrap of X. Okay, browse W. It will tell me it's a chunk. So the browser knows the type but it will not do anything that the language doesn't let me. So the language can tell me what is the type. So the browser knows that it's a chunk, which is a limited record, and so it's a record, so it says that it's like a record, there might be stuff inside. So it's telling me that, but I don't know what's inside, okay? So I have no idea what's in there in this W. It could be anything in there, okay? The only way to find out is to do unwrap. Then I get 23 again. But if I don't know unwrap, there's no way I can find out. I cannot find out what's inside. Okay? So that's actually a very important thing. Let me, okay, so that's good. Let me go back to the slides now. Okay, so this shows you then how to build secure abstract data types, using secret keys and boxes like that you can lock the secure records. So if your language does not support those things, then you cannot implement what I'm showing you here. So there are many languages that do support abstract data types, but they do not show this, what I'm showing you here, to the programmer. So all of the internal mechanism that I'm showing you here is hidden, okay? But that's not good enough for this course, In the course, I want you to understand how these things can actually work. So it actually needs new language concept, Okay. So let me make another comment. So new name returns a fresh new name, Each time you call it, it returns a new, different name. So it's not declarative, okay? It's not a declarative function. Because if you call it twice, if it would be declarative, you call the same function twice, it returns the same thing, But here, each time you call it, it returns something new. It's a new, fresh name. But you can still use it to build declarative data abstractions, okay? So here, this thing, the stack here is declarative. And the reason is that all you have here is constants. There's no mutable state. And the key, it's only when you create the data abstraction that you create a new key. While it's running, you don't have to create new keys, okay? Of course, you can use names in very clever ways. You can actually build secure protocols by creating new names on the fly while the programming is running. Okay, so in a networking protocol, this is sometimes called a nonce. A nonce is like a new fresh key that you create just once. But here you're using the same key. Once the abstraction is done, you always have the same key in here. Okay, so it's still completely declarative. Okay, let me make some remark now on abstract data types. So this, what I'm telling you, is not new. It's actually very old. So there are languages that are not object-oriented, but are abstract data type languages. Okay? And the first one is called Clue. Probably nobody remembers it. So this was developed by Barbara Liskov. So Barbara Liskov was one of the founders of data abstraction. The substitution principle is sometimes called the Liskov substitution principle in object-oriented languages. Remember that if a function takes an object, it also has to work with the subclasses of that object. That principle is very important. And that principle was discovered also by Barbara Liskov. Okay. And she also won the Turing Award, which is the Nobel Prize for computer scientists. Okay. So the first languages using abstract data types was developed in 1974. That's a long time ago, The early days of computers. Actually, it's only a little bit later than the first object-oriented language, which is Simula 67. So objects and classes comes from Simula, okay? And then later on came Smalltalk and C++ and Java. But these languages were the first, okay? Clue and Simula. So this Clue language let you build new abstract data types. The same way Java lets you define classes, in Clue you can define new abstract data types, okay? And in fact, if you look at Java, Java is not a pure object-oriented language. A Java integer, Java objects are also partly abstract data types, which is very weird actually. People sometimes don't know it. So two Java objects that inherit from the same class, they can look inside each other's attributes. That's kind of weird for object. Normally nobody can look inside. But if they have the same parent class, they can do it. That's kind of like an abstract data type. So Java objects are actually mixing abstract data type and objects, okay? So the abstract data type concept, it's not disappeared, okay? It's very strong and alive today. And usually people talk about object-oriented languages, but in fact, object-oriented languages are just as much abstract data type languages, only it's not mediatized. So a better thing would be to say that they're data abstraction languages, okay? So programming languages today, they learn from these ancestors so that you can use them to build data abstractions. So instead of calling them object-oriented language, you should probably call them data abstraction languages, huh? Because they also support abstract data type, even if they don't say it, okay? So that's a final remark. So abstract data type, it's not like a contest where it was abstract data types fighting against objects and one of them won. No, they both are fundamentally useful, and today's languages are using both, okay? Okay, so that gives you, I hope, a good idea of abstract data types and how to build them and what they mean actually fundamentally, okay? Okay, now I want to say a few words on objects, but you know objects already, so maybe I can go faster here, okay? So objects, a single object represents both the value. So there's not like 1 plus 1 equal 2, no, the 1 is an object and the plus is part of that. So in the stack, you can say S push X, or S pop X. So you give it the operation. So there's only one thing, actually, which is S. It's not like you have operations, push, pop, which are functions. So the way I defined them before, if you look here, push is a function that takes a stack and returns a stack. So the push and the stack are different. Here, there's only one thing, S, and you can tell it to do a push, and the push happens internally, okay? So the stack value is stored inside the object, okay? So that's the basic idea, but I do want to give you the semantics of it very quickly to refresh your memory, okay? So if you want to define an object semantically, most languages, they give you syntax for that. They let you define a class and methods and do new object and da-da. But that's not telling you what it means. That's just syntax. So you have to define it in terms of the primitive operations. So here is a definition of a stack object, okay? So this function new stack will return a stack object. So an object is represented here semantically as a one-argument procedure. The argument is usually called a message. You have the funny terminology of object languages. M is the message, and these three operations, which are the case, so depending on the value, the message, push X, pop X is empty, I do a different operation. So these operations are usually called methods. So of course the object-oriented, if community has to define its own words for these things. But the operations are called methods, and the actual argument here is called message to the object. So this object has a state inside. So you see it has a cell, which you can update, and the push operation, so this is actually usually called an attribute in an object-oriented language. So the attribute would be the internal value of the stack. You do push x, C will get x bar previous value. So this is the previous value of the axis of the C, x bar, and this colon equal is an assignment. So here I'm basically updating the state, okay? So each call to new stack will create a new stack object. So you can see there's only one thing here, these one argument procedures, and the operations are inside them. So here you've combined the value and the operations. So the value here is this nil thing, and these three operations are combined together. So the object is a one argument procedure, and here it's doing what's called procedure dispatching. So there's something that object-oriented languages do, which is called dispatching, which is when you send a message to an object, it chooses the method. So there's many ways to do this. Here it's a case statement, but you can also look at the types. You can have messages that have integer arguments or real number arguments or whatever, and then it will choose the method. So there's different ways of choosing the method. And the hiddenness, the protection, so the internal value again is protected here. Yeah, question?
Why not send a record with all the mapping with functions?
A record?
Yes, we can return a record.
You can return a record. Yeah, that's another way of doing it, yeah. So that's called record dispatching. So you can, here I represent the object as a one argument procedure, but you can also represent the object as a record. And each field of the record is one of the operations, okay? That's another way, it's just as good. So there's different ways, but the point is you have to combine them all into one thing here. So here I combine it into a procedure, but you could combine it into a record. So I'm not going to show you that, but it's in the book, and maybe I think you saw it in a previous course. Okay. So here we do not need these secret keys. So maybe you can see it's a little bit simpler, but you do need cells here. Okay. Using cells. Okay. Here it's nice to compare them. So here is I think this is going to the question here. So here is the same stack as an abstract data type and as an object. So this is the code I showed before with the wrap and unwrap. Here I have a cell. Here, instead of a procedure, I return all the operations grouped together into a record. Okay. So this is another way to represent an object. It's different, and the interesting thing is now you can actually see what are the methods. Okay, so you can see that it's the same stack, but here everything is together. There's one thing, and here you have separate. I have the push and the pop and is empty are separate from the stack values. You give W to a push, and it returns a new W. So in fact, any data abstraction can be one or the other. There's no limitations like that, okay? Okay, so maybe some historical comment again. So remember I mentioned Simula 67. Actually, if you want to look at Simula, it's actually amazing. You look at it, it looks very modern, okay? It's like not so much was invented since then. The syntax looks really modern if you look at Simula 67. And after it came a language called Smalltalk, which was over 10 years, starting in 71, and C++. And those two languages were influencing all the big modern object-oriented language, Java, C#, Python, Ruby, and so on. So all of these modern languages actually it's better to call them data abstraction languages because they have both objects and abstract data types in there. Okay? Okay, now I want to say a few words on the fact that there's 4 kinds of data abstraction, and I want to show you especially functional objects. They're a very special kind of object, and they start to be very useful in cloud analytics. So this is not just theory, it's actually used in modern systems. But let me make a small break now, and then I'll show you the weird, the exotic data abstraction. What I showed you now was the normal ones, okay? But there's some weird ones that are not so much used, but it's interesting to see them. So I showed them to you after the break. So we make a small break. So let me finish now the abstraction before we go to multi-agents. So far, we've seen these 2 abstract data types, which are declarative, and objects that have cells inside, they're non-declarative. This is the most common ones. But there's 2 other ones that are kind of weird. Well, weird because languages don't really use them, but it's interesting to check them out. You can have abstract data types that have state inside, or you can have pure functional objects. So those are actually very interesting, these pure functional objects. So that makes 4 in all. So if you make a graph, so here on the horizontal, you can see whether the things are grouped together, which I call bundling, or whether, when they're grouped together objects, and when they're separate, they're abstract data type. And here it's whether they have no state, or no cells, or cells inside. So you have these 4 different kinds. So this one is like Java integers, this one is like Java objects. But here, these functional objects are funny. Now, used to be that nobody used them. So this is exactly like Java objects, but there's no, you cannot update them. It's weird. So I will show you how these guys work. So in modern big data analytics tools, these are actually used. And the reason why they're used is because they're transmitted around the network. And so it's very hard to update an object when you transmit it, because everybody has to see the update. Okay? But if it's a functional object, then it's like a constant, it's not changing. So you can very easily copy it from one computing node to the other. So on a big cloud analytics tool, where you have hundreds of machines connected together, regular objects are actually complicated to do. Because if you update them, everybody has to see the update for consistency. But if it's a functional object, you can just copy them around, and they can be pipelined around. So this is called fluence. So actually, the Scala language actually supports this in the syntax. But these used to be very weird data abstraction, but it's nice. In this course, I'm showing you the whole spectrum. And it used to be, years ago, let's say 10 years ago, that this was not used. But now, in 2020, 2021, you can see that this actually is coming up as a really interesting new kind of data abstraction. So if you use the cloud tools, so if you take the cloud computing course, actually, even though you're not talking about it so much, these platforms are starting to use this thing inside them. Okay? Things like Apache Flink and so on. Okay? So functional objects, so they're like objects, but they're pure functional. There's no cell inside. There's also stateful abstract data type. But let me just focus on the functional object, okay? So this is now the same stack as we saw before, but implemented as a functional object. So this is actually, the code looks very simple, but it's actually very interesting. Here I have a function called stack object, okay? So this stack object function here, so the end is here. is this thing, and internally it has the operations, so it returns a stack. So it's like an object, huh? It's a stack with several operations. Push, pop is empty. But when I do an operation, when I do push, for example, I don't update the cell, I create a new stack object. So I give a stack object, so I have a stack object here which has nil inside. If I now do a push on this, it's going to return a new stack object. So the original stack object does not change. So this is actually very, very interesting and very kind of strange. When you update an object, usually the object is changing. Here the objects do not change. But when you update an object, you create a new object. So push will call stack object to create a new object with a new stack inside. Or pop will call stack object with the pop stack inside. Okay? So whenever I do a push or pop, I'm creating a new stack object. Okay? The interesting thing also about this is that it's in the language, it's very simple. I don't need cells, and I don't need the secure wrapping. So in the previous one, abstract data type and regular objects, I needed new extra language concepts. I needed cells to do objects, and I needed names and secure wrappers to do the abstract data type. But this one does not need any of that. It's just a pure higher order program with static or lexical scoping. Okay, that's all it is. It doesn't need any other language mechanism. So in some sense, functional objects are the simplest data abstraction. It's kind of funny because for many years, no languages were using this. But now, this is starting to become used. Okay? So I'm not going to say so much more about this, but if you use cloud tools, you should be conscious that these functional objects are going to be inside that. So there is a recent language called Scala, which has, it's like an evolution of Java. It has both functions and objects, but we can define an immutable object that returns another immutable object. So these are exactly, so what in Java is called an immutable object is exactly the function object I showed you. Okay? So in Java, you can define immutable objects which are exactly functional objects. And the Scala notation is sometimes used for big data analytics tools. So this is a modern trend to going toward functional objects. Okay? So that's something I wanted to mention to you so that later on you won't be surprised when you see these kind of weird objects, these functional objects. The other one, the fourth one, is a stateful abstract data type. This is another weird one because it's an abstract data type, but it's not a constant. That means it's a box with a value, and if I do push, I change the value inside, but the push and the value are still separate. So I do push of a stack, I unwrap it, and I change it internally, because internally there's a cell. So it's very funny, it's a wrapped cell, in a sense. So when I create a new stack, I do wrap of new cell. And when I do push, it's not a function, it's a procedure. Because I push an element on the stack, so E is a new element on the stack, S is the wrapped stack. I get the unwrapped, but C, it's a cell inside. Then I update the cell. So the abstract data type values are not constants. I'm updating them inside the abstract data type. Okay? So this is also a data abstraction. It's called a stateful abstract data type. So it's using both a secure wrapper and a cell. Okay? Notice that I'm almost never using wrap. It's always doing unwrap. The wrap, I needed to create a new stack, but push and pop, they don't need to do wrap anymore because they are modifying the cell inside, so they don't have to create a new value, so they don't need to call wrap, okay? So the wrap is only called when I create a stack. So that's an unusual kind of data abstraction, but this one is actually not really so much used today. Maybe someday, okay? You can program with this kind. So sometimes people program in C using these kinds of things. But this one is actually still kind of an orphan. So this fourth one is still kind of an orphan, but the third one, the functional objects, which used to be an orphan, is now actually really a lot used. So who knows? Maybe in 10 years these will be used too. Okay, so let me finish on data abstraction. Just to summarize, so there's 4 kinds, 2 axes, so there's objects versus abstract data types, and each one can be either declarative or non-declarative. We show you the semantics of them. Huh? So the code I'm showing you is defining them in terms of primitives. So actually, that gives you this actual semantics of it, because you know the semantics of the primitives. So we showed how they're built, static scoping, higher order. For abstract data types, you also need these unforgeable keys, and you need these secure boxes. But the unforgeable constants are very important. And then the fourth one, so there's 3 of them that are used a lot, but there's a fourth one that's not really used. Okay. So that's all I want to say on data abstraction. So that's important because I want you to understand the secure part, especially. Okay, so now I want to go to the next part of the course. So the next part of the course, we're going to talk about multi-agent programming. So in this course, we're going to talk to you about agents that send messages, and at the end of the course, we're going to talk about shared state concurrency, things like monitors and transactions. So those are the 2 big paradigms for concurrent programming. Okay? So now I want to talk to you about multi-agent. So this is used a lot, and there's an industrial language that uses this, which is called Erlang. So we're going to talk a lot about Erlang later on. But first I want to show you how to do this. I want to show you really what it's about. So I want to compare this with the data flow that we did before. Okay, so we're going to see a bunch of stuff here. This is called multi-agent programming. It does message passing. It's based on ports. Remember, ports is a kind of communication channel. You can do send and you can read the port. Remember we saw you can do client server with ports. But with a port you can actually build an agent, which is kind of like an object, but you send it messages. Okay? And this is called a port object. And you can have all kinds of message protocols with this. We saw some of this last in the 11th Zeophyr, the previous course, okay? You can define message protocols. But now I want to show you some new stuff. I want to show you, first of all, I want to compare multi-agents with deterministic data flow. So I'm going to show you this kind of very nice problem called Flavius Josephus problem, and we're going to write programs both using active objects and deterministic data flow. So active objects are like port objects, except they're defined using classes. There's like real object-oriented objects inside. But in fact, it's very similar. It's like an agent that receives messages. And then finally, I'm going to show you how to write big programs. So if I have dozens or hundreds of agents talking to each other, how do you organize that? It's extremely concurrent. They're all sending messages to each other. So you have to kind of do it in a smart way, otherwise it gets really messy. So I'm going to show you how to do that. And then I'm going to show you a bigger, complicated example called the lift control system. So lift or elevator. So like when you go into a big hotel, you can have many elevator shafts going up and down. You can have 20 floors and people pressing buttons all the time. Anybody can press a button anytime. You can go from any floor to any, and the lifts are always going up and down. So this is a large multi-agent system, okay? So we're going to show you how to program this realistic kind of system. And real lifts in hotels are doing something similar, okay? So that's going to be a bigger example, but we won't be able to do it today. But hopefully today I can talk about Flavius Josephus. So the first thing is I want to refresh you on port objects. So it's basically an agent, and you send a message, and it has internal state. So we saw already a little bit how to do this. So there's an agent, and it's a concurrent thing, and it has an internal memory called the state. So it starts with an initialized state, and whenever I receive a message, I do a state transition. So this is actually semantically what it's doing, okay? Whenever I receive a message, so M1 is a message, there is a function which takes the original state as 0 and updates it and turns it into a new state, and it keeps going. So internally, it's a sequence of state update. So you can see that internally, it's actually sequential. I can send messages to this, and the state will be updated. So with each message received, the state will be updated, and there's this function which defines it, called the state transition function. So it takes the state and the message, and it returns a new state. So the whole behavior of this thing is defined by this function, f. Okay? Okay, so you can create these pretty easily. So here is a generic function to create these port objects. So here I have new port object. It has an initial state, and f is this state transition function. Internally, it has this loop, and the loop will take a stream, because in fact there's a port here. So all the messages will arrive on the stream of this port, and whenever I get a message M, it will do f of state M. So this is the state transition, and then it does a recursive call and it waits for the next message. So this is actually the internal behavior, it's this loop. So the actual port object is a thread, so I create a new thread here. In this thread I have a port, P, okay, and I can send messages to this port, and they will appear on the stream whenever I send. And then I have this loop that will update the internal state. So it starts with init, state starts with init, and each time I receive a message, it will update it. Okay? So that's a stateful port object. So this is the function, but I want to do a little bit of thinking before we start programming with this. I want to reflect a little bit on this code. So this code is just doing this. Okay. So this is like mathematical definition. And here we have the code that implements that definition. But this code is kind of, it should be kind of familiar. This code actually, if you look at the loop function, the structure of the loop, it's actually a function that we know in some sense, okay? You start from an initial state, you apply f to the previous state and a message to go to the next state. And f is a binary operation. So it's like you're accumulating these binary operations, okay? So this function is actually something we know. This is actually an important function. It's not just some random function. It turns out this is an important function, okay? This function is something we know, and you should, if you do functional programming, you should see that this is something that you know. So this is actually a fold. Remember this fold operation? Fold is a funny operation. It takes a list and a binary and it folds everything down to one value. Okay? This is actually doing the same thing. It takes, so instead of a list, you have a stream of messages, but it doesn't end. So it's like a fold operation that never ends. Okay? And each time it adds in the new message into the state using the state transition function, which is binary. Okay? So it looks like this. So remember the fold? So this is fold. It takes a list, which I call S here, binary function F, and U, which is an accumulator. So the U starts out to be some kind of a unit, and each time I bring in an element of the list, like A0, I update it with F. So I have U, F, A0. So the F could be a plus, and this could be an integer. So I'm summing things. So 0 plus A0, and then plus A1, plus A2. So each time I bring in new elements, I'm folding them in. So that's why it's called fold. I'm folding them into the accumulator. So this is exactly the same function as the port object. So this loop, so this is the heart of the port object. I have a thread, I have a port, and I have this loop. But I can replace it. I have a thread, I have a port, this loop is actually a fold, and F is an argument. Okay? So this is, I can replace it. Actually, it's not exactly, there's a small bug here. So you see what is the small bug, right? Yes? What is it? I mean, it's almost right, but fold is a function, and loop is a procedure. Fold actually returns a value, because normally the fold works on a list, and when you finish the list, it has calculated the full value, okay? So actually you have to, you return some value here. So this, we could define the new port object like this. So we don't actually have to define the loop, you can just use fold. So it's like one line definition here of the new port object. So you can see I'm combining a thread, a port, and a fold. Together they make a port object. You can see it's interesting to see how you can combine these powerful concepts to build new things. This out, I put it here because the fold has an output, but it actually means something for port objects too. Assume that the port object, it could terminate. So in the streams here, the stream will never terminate. There's never nil. But I could have a version of a stream where it terminates. So it's like I'm closing the stream. And out would be the final state of the port object when the agent terminates. So actually the out actually has even a meaning there. Even though I didn't originally think of it like that, if you have to put it here because fold is a function. But it actually has interesting meaning, you see? So it actually does something nice in terms of port objects. So this port object will never terminate. This fold will never reach nil, because the stream never terminates. But maybe in some other design it might. So if the stream terminates with nil, then the port object itself will also terminate. So that's a reasonable way of closing the system, okay? So the out actually also means something. So this is actually a nice definition of port object. We're going to use it. We're going to use it now. So this is a little bit of a refresher, because we saw some of this. Yeah, question?
Let's imagine the stream can close, and then we want to have an access to out. Could we imagine new port object returns a tuple including P and out, so we can access it? Or
yeah, if you assume this closes, then you might want to get access to the final state. But this function actually returns the port itself. So you need a second output, in fact. It could be another output here. So if you want to access the terminal state, you would actually need a second output. So you would need to change it. But it's very logical, actually. It would be a very nice thing. The second output would give you the terminal, the state when it terminates. So when it closes. So that would be very nice. It manages very nicely, in fact, because sometimes you want to close, you want to terminate. So a thread is actually overhead. It has state, it's using memory and CPU. So when the stream terminates, everything will terminate very nicely. The thread terminates, so the fold finishes. So you go to the end, the thread will terminate, so the memory is recovered. So the only thing that's left is the out. So yeah, so that would be a very nice thing. So right now I'm not worrying about the termination. I'm assuming these port objects, they live forever. But they might terminate. Yeah?
Les messages qui n'ont pas besoin d'être rajoutés dans une queue, ils peuvent déjà être traités parce qu'il n'y a pas de restitution dessus.
Tu veux une autre version où les messages peuvent être traités dans un autre ordre?
Avoir une option qui dit, voilà, ce message ne doit pas être rajouté dans la queue parce qu'il peut être traité directement.
Ah, tu voudrais avoir des messages de haute priorité.
Oui.
So the other question is, you might want to have multiple input queues, high priority, low priority. Actually, I don't know why if you asked this on purpose, because Erlang does something like that. So Erlang is a industrial languages based on these agents, which in Erlang are called processes, but they have a single thread inside, and they accept messages. But they're slightly different from port objects, because the messages are put in a mailbox, and you take them out using pattern matching. So you can actually have high priority messages that bypass the others. So it's a little bit more sophisticated than a port object. So yeah, so we get back to that when we talk about Erlang, huh?
All right.
Yeah, so this is the simplest form of agent, where the messages are treated in the order they arrive. They're treated one by one, but maybe you want some messages to be treated before the others for some reason. They have high priority messages, okay? So this will not let you do that. But in an Erlang agent, you can do that. But we'll talk about that later. So this is the simplest form of agent. It's very simple. But of course, in a realistic language, you might want something a little bit more sophisticated. So this one is okay for many things, but sometimes you want a little bit more. You might want to have certain messages that are like management messages that come in and that have priority over all the other messages to do things, like maybe you want to change something in the port object or to close it or whatever. So this will not let you do that. This is like a very simple form of agent. Okay? Is that kind of the answering? So, but later in the course we will talk about Erlang, which is a agent language. And the Erlang agents are like port objects, but they're a little bit more sophisticated, actually, okay? So they have a little bit more functionality because the Erlang is a very practical language. So it's very interesting then to compare the Erlang agents with these ones. These are very simple, and you can define it in one line. The Erlang you cannot define in one line, it's more complicated. But for programming, it's very nice, the Erlang agent. And we'll see it later in the course. So this is just the first version of what we get. So remember, now let me give a refresher. Remember, we did message protocols. So this is not new, if you remember the course 1104, which probably most of you took. So we saw port objects, and we saw message protocols using them, okay? So a message protocol is a sequence of messages between two or more port objects, but that together it has a meaning. It has a higher level meaning than just the individual messages. For example, it could be a send and a return from client server. So you have two messages, but actually it's one request, okay? Or you can have multiple messages going back and forth, that actually are one thing in a higher level language. So remember, I just want to show you this picture, what we saw in the previous course, to refresh a little bit your memory. So we saw RMI, so this is just send and return. We saw asynchronous RMI, remember? When you send two messages and you wait for two results to come back, and they can overlap. Okay, we saw RMI with callback. This is when you send a message, but the server needs to get some information from the client before calculating an answer. So inside this message, there's a small return request here, which is the callback to the client. And there's different ways that you can do this, so you can do it with threads or continuation. And here is the complicated one we saw, the most complicated one, where it's the asynchronous RMI, where you can have two overlapping ones, but they're both doing callbacks. So there's lots of things going on, but conceptually it's a very simple thing, okay? That conceptually, an asynchronous RMI with callback is just a client asking the server for something. That's all it is. But sometimes that requires multiple messages, okay? So these multiple messages actually have a higher level meaning, okay? So I'm not going to go more into that here. This is something we saw in the previous course. So I don't expect you to remember all the details, but I expect you to remember the idea, what we were trying to do, is to show how to do different kinds of message protocols. So you remember a little bit what we did in the previous course? You could do. So many people took here 1104, right? Most of you? Anybody did not take it? Ah, that's good, okay. So most people, but even if you did not, it's not so important, but it will help you understand the rest. So now I want to talk about Flavius Josephus problem. So this is a really neat thing, actually, which I like a lot, because I like a lot of historical stories, okay? So this is a historical thing. You can actually look up this guy. You have wrote many things, okay? So he was a Roman historian, but this was during the time when Rome invaded Palestine, and so he was actually Jewish, and so it was a big war, and it was not very nice, okay? There was wars going on. So, but Flavius Josephus was actually a smart guy, so he was in a cave, surrounded by Roman soldiers, together with his fellow soldiers, defending his thing, and the Romans were attacking. Somehow he survived, and he became a Roman citizen, and he wrote memoirs, and he became like a smart patrician. So he made a good career in Rome, okay, so the guy was very smart, he didn't die. But the anecdote is here, and he wrote this up in one of his documents. So he was in a cave with fellow soldiers, and there were 40 men, and they were lost. Okay? It was over for them. So they decided to honorably, they would not be killed by the Romans, they would commit suicide. So this would impress the Romans, okay? So they were standing in a ring. So the idea was that they would count every third man, 1, 2, 3, and that guy commits suicide. 1, 2, 3, and keep going until nobody's left. Okay, so Josephus was one of these guys. He didn't really want to commit suicide, okay? So somehow he managed to place himself in the position of the last survivor. So he was the only one left at the end, okay? So that was very smart. So he had to figure it out. And of course, while they were doing it, I'm sure he was very meticulous. They were not making mistakes, okay? So that it would come up to him at the end. So he was the last survivor, and he did not commit suicide, obviously. And he survived, and he became a famous Roman historian. He wrote his memoirs, and those memoirs are still existing today, and you can read them. So the guy made a good career, okay? So, but there's an interesting problem here, huh? What is the position of the last survivor? So, we can actually make an interesting problem from this case. So you have n soldiers, and k is the number of steps you count. So here I have 40 soldiers, and you count 3. But you could do it for n and k. So you can actually define a program that solves this problem for any k, n and k, and tells you what is the position of the last survivor. Of course, Josephus didn't have that ability, but now we can do that, and you can even do it for thousands of soldiers in very complicated cases. So it's actually a very interesting function, and mathematicians have studied this function and so on. But let's just look at this program. So we're going to make a protocol, a message protocol, to solve this problem. So there's a message circulating around the ring. So here is the message. It's kill message with 2 arguments, x and s. X counts the number of live objects that are traversed, and s is the total number of live objects remaining. So if you start by passing kill 1n to the first object. So the first object that you traverse, 1, okay, and so you are on 1 first live object, and there are still n objects alive. And then when an object receives kill xs, it follows a set of rules, okay? So if it's alive and s is equal to 1, yes, we're done. It is the last survivor, okay? If it is alive, i.e. an x mod k is equal to 0, so it's a multiple of k. So for Josephus' case, 1, 2, 3, poor guy who receives that message, okay? It becomes dead, okay? And it sends kill x plus 1 to s minus 1 to the next object. So it has traversed one live object, because you have to keep counting them, but there's one less live object after, so s minus 1. So the message circulates. So if it is alive and x mod k is different from 0, then it doesn't have to commit suicide, but it did traverse one live object, so it sends kill x plus 1 s, not s minus 1, but s to the next object. So you see this message is circulating. Now, if the object is dead, then it just forwards kill xs to the next object. So if it's dead, it's like a zombie, okay? It has to still do something, yeah? If it received the message, it has to forward it. So we have this topology of n objects, okay? Now, I want to show you a deterministic data flow program for this, and I want to show you an active object protocol for this, okay? So I'm going to show you 2 pieces of code, okay? So we're going to show 2 implementations of this. So an active object, which is like a port object, except it's defined using a class. And each method is the message. So there will be a kill method. So each soldier will be an active object. Okay, there's a class, which I will call victim. It defines a kill method that implements the Josephus protocol, depending on the position of the object, okay? And there's an initialization, of course, that builds the ring initially, okay? Now, I'm going to do a deterministic data flow implementation again. So here, each soldier is what we call the stream object. So it's basically receiving a stream and sending a stream, like we saw for Hamming and for the other things. It receives a stream and it sends a stream. And the function, the victim is a function, it's not a class. It reads a stream of kill messages and it outputs a new stream. So it's reading these kill messages, and depending on which soldier it is, it outputs other kill messages, okay? And you have to build a ring of these, of course, which are connected in a ring, and then the kill message will circulate in both cases, okay? So you can actually build this in both these 2 kinds of paradigms. Notice these very different paradigms, huh? They're very different, but I want to show you now the code for them. But we won't have time today to show all the code. But let me show you first this code here, the active object, because it's very intuitive, okay? This one is very intuitive, and you can see how it works. And then, next time we'll see this code. It's actually interesting, because they're both doing exactly the same, but the code looks very different. But actually, if you think a little bit, it's not that different. There is a correspondence between these two very different paradigms. And another interesting thing is that the deterministic data flow code is much shorter. It's only half the size. So this is actually a very compact code here, okay? So let me show you today, I just want to show you this active object implementation. So you get the protocol, huh? You're getting it what it is, huh? So let me go to the, okay, here's going to be Flavius Josephus. So first we need to define active objects. So they're very similar to port objects, except it's defined using a class. So it's like real object-oriented programming. So I'm not going to explain too much how that works, but you will see it when we do the, okay. So this is the class implementing it, the protocol. So inside the active object, I will have an object of this class, and it has some attributes already. So some things it knows from the beginning. So it starts, there's an alive, which is a Boolean, it starts being true. There is the step, so this is how many you go before committing suicide, which is K. There is a global variable last, which is the L here, okay? And then there is okay, the identity of the object, so the number of the soldier, okay? So there's this method is a set successor. We need this when we build the ring. So we're going to build a ring of these, huh? 40 or whatever of them, huh? But here's the kill method, which I show you now. So kill XS. So now this if statement here is just a protocol I define. So if the object is alive, is that on purpose? That's weird. Okay. Zombies are around somewhere. Okay. So if the object is alive, if it's not alive, then I just send kill XS to the successor. So this successor attribute is pointing to the next object in the ring. Okay. So if the object is dead, I just forward the kill message. But if it's alive, if S is equal to 1, then I'm done. And last here is actually a global variable, L, which is going to be bound to the last survivor. And the last survivor is me, the identity. So I bind L to this. So the global variable will be bound to my identity. So this is only going to happen once because there's only one guy at the end. Huh? So then the next two cases are following the protocol. If X mod K, so the step is 0, then alive is false. That's the committing suicide here. And I send kill X plus 1, S minus 1 to the successor. Otherwise, I send kill X plus 1, S. So S minus 1 is how many alive are left. Huh? If X mod step is different from 0, the S does not change. Okay, so that's the victim. Okay. So this one is doing the initialization. So just to make things simple, I'm using an Oz data type called an array, which creates n. It's basically a vector with n elements. So first I create n objects. For I, from 1 to n, I do a.i, so that's the array, from 1 to n. I create a new active object of class victim, and the initial state is I is the identity, k is the step, and last is this global variable. So you can see this is a function Josephus with n and k as arguments. Last is a single global variable that will be bound by the last survivor. Now I connect them into a ring. So I have to be careful because they go from 1 to n, but the n has to connect to 1. Huh? So if I go from 1 to n minus 1, then A dot I, the successor, is A dot I plus 1. But for A dot N, the successor is A dot 1. So for the last one, I have to connect it to the first one. Huh? But all the other ones I can do it in a loop. And then to make it actually run, I have to stick in an initial kill message. So A dot 1, kill 1N. And then this returns the last. So that's it, that's my program. So what this last message here sent is what starts the thing running, okay? If I don't do this, nothing's gonna happen, it just sits there. But if I put a kill message in there, then it will start circulating, and eventually the last will be bound, okay? So that's the Josephus. Okay. So I do Josephus 5-2, and it is 3. Is that reasonable? Well, let's try. 1, 2, 3, 4, 5. Now I'm doing 5-2. Huh? So 1, I remove 2, I remove 4, I remove 1, and I remove 5. So the final one is 3. Okay? That seems reasonable, huh? It's printing 3. Of course, now I want to tell Josephus what he should have done, but he knew it, of course. Huh? 43. So this one gives me 28. So if he puts himself in this position, which I'm sure he did, he would survive. Okay? So that's the Josephus written as active object. And of course you can run it in more in a more important case. Let's say I have 1,000 soldiers, and every 100, that's more complicated, huh? You see, it takes a little bit of time, huh? It's number 876 is the survivor, okay? So that's Josephus when I'm doing active objects. So you can see the code here, huh? You see, the code is very reasonable, right? I mean, it's understandable, right? You get it, huh? And it's doing exactly the protocol we did. You can understand this code too, huh? How we create an object, we build a ring here. So it's not complicated, right? It's clear, huh? And it works, okay? And it's doing the exact protocol. So now the next thing is, let's do the same thing purely in deterministic data flow. And the code is really, really different, you'll see. It looks nothing like this at all. It's totally different. And then we compare the two. And then I think you will really see, you will feel the difference between the two paradigms. Huh? So this is an airline programmer who would do this. Huh? But a functional deterministic data flow programmer, he would do something very different. Okay? So, and you will see that next time. So you can actually look ahead if you want, because it's in the book, the example. Huh? But you see the code is very different. So it's, I think, a great example, because to compare the two, how does this compare to a data flow? Okay, so let me stop here, 10:30. And so I will fix the date for the midterm. So maybe today we can already fix it. So then I will arrange for finding an auditorium, okay? And next course, which will be in 2 weeks, we will finish this and you will actually see how the two paradigms compare.